type state, obviously it's a bit niche, right? So when should you consider using it? Well, one, when your program behaves like a state machine. You have like specific states between which you can transition, so you want to enforce this transition at the state compile time level. The second, when you have mutually exclusive systems. So in our case, we had engine system and infotainment systems, which we really want to keep separated, right? So this type state allows us to achieve this really nicely. The next thing is perhaps you want to enforce a strict order operations. Remember when we showed the example where the file must be opened first before you can read it. So if you have such use cases, type state is your friend. And yeah, so like this is the same thing. Manage resources with open-close semantics. This could be like files, cameras, connections, socket connections, whatever. Hello everyone again. My name is Alex. As I said, flew here from London, originally from Ukraine. I work at American Express and I maintain a technical blog at Swiftology.io. So today I'm going to talk to you about the new design pattern which is made available in Swift 5.9, which is called Typestate. Now, we're actually going to cover a few topics today, 3 to be more specific, and they all kind of related and they all combine into this nice idea of type state, which is like essentially type-safe state machines. I hope everybody loves state machines. They're pretty amazing overall, but now they're even better. We're going to talk about context-aware APIs, which you can achieve with generic constraints. So that's something you can already do, even before Swift 5.9, but that's another thing that adds the power to type state. And then we'll get to meet the borrow checker that was introduced in 5.9. And there's also another talk tomorrow, which goes into more detail about the borrow checker. Now, without further ado, let me introduce you to like what is the type state in general. Now, if you look at this code, it should be very familiar to everybody, like the behavior, I mean. So we declare a variable, could be any variable. Then inside of one logic branch, we instantiate this variable, like we assign a value to it, in this case with Swift Heroes. And on line 4, we can actually do something, right? Like we can lowercase, you know, we can operate, call functions. But in the else clause, Swift would actually give us this, you know, very familiar error. I'm sure you all saw this, which is like, oh, hold on, you're trying to call functions on this variable, but you haven't instantiated yet. Now, this all seems like very familiar, and we could, you know, forget about, you know, get used to it, but how does it actually work? So there's something under the hood of the Swift compiler that makes it possible, and this something is called type state analysis. Now, the way it works is the compiler actually analyzes the lifetime of our code, and it looks at the code and it assigns state, or in this case type state, for a variable throughout its lifetime. So on the first line of code, it's uninitialized, right? Then on the line 3, it is initialized. And line 4, since it is initialized, we can call functions on it. But on line 6, it is still uninitialized. So the compiler is able to kind of break down this code, analyze it, and hence produce this compilation error. So this is all super cool. But what if I told you that type state doesn't have to be limited to initialization only? What if we could have an analysis on other states? For example, if it's a file, we want an analysis of is it open or closed. So same idea here, like on the line 6, we would actually want to get a compilation error saying like, oh, well, you can't read the file before you open it. It would make a lot of sense, right? Well, Swift can't do this. Or can it? Let's see. And you know, the type analysis would go like this. It's on the first line it's closed, then it's open, hence we can call read. On line 6 it's closed, hence we can't. So this is the idea is clear now. How to achieve this, we'll see. Now, type state isn't some new weird idea. This is the Swift repo, and one of the documents is actually called Typestate, dating back to 2011, so like really ancient times, when Chris Latner, the creator of Swift, actually created some notes on adopting the Typestate within Swift, like since day one. And he made some great points there, so you'll see, you can go and read. Now, I think the best way to understand the idea is to look at the practical example. So I have a business plan. I want to build an electric car. And you can see that it is an electric car because there's like, electric bolts on sides. So, and yeah, every business idea starts with on a napkin. Now, my greatest competitor is Tesla, and I want to crush them. So Tesla has this cool feature where you can play video game using your steering and pedals to control the car. Now, obviously, using the actual car controls to play a video game kind of comes with a bit of a risk, right? Like if I smash the acceleration pedal, I don't want the car to take off. So then the way you can use this game, you can only launch the game when the car is in a park state, right? So we need to check this state very carefully. And you can also, if you smash the acceleration pedal, it does nothing. So only the brake pedal works in this game, and the car accelerates on its own. Now, I want to implement the same functionality in my car, but I want it to be better than Tesla because I don't want my cars to crash. Now, let's look at the simple state machine. We start in a parked state. When we are in a park state, we can launch the game, which transitions us to the game mode. We can exit the game, which brings us back to the park state. In the park state, we can switch to drive, which allows us to actually drive the car, and we can switch back to park. Notice that drive and game are mutually exclusive states, which is really, really important. Like, we never want to launch the game while we're driving, and we never want to start driving while we're playing the game. I hope everybody agrees on that. Now, the naive approach, or like the traditional approach to implement this, is like, let's create a car struct. This would be like our computer, right? And the state enum, it enumerates the states, drive, park, and game, simple enum, and we start in a park state with like a local variable that we change. Now, we need a couple of more systems. One is the engine system, which allows us to start an engine and stop the engine and also accelerate and brake. And there's another system, which is the infotainment system, which allows us to launch the game, exit the game, and also brake within the game, right? So these are the underlying systems that our car computer needs to operate. Now, important thing is these both are classes, so reference types. So we have the properties. We have references to these systems, and these systems are kind of like singletons in a sense, right? There's only one engine system and only one infotainment system. Okay, so let's implement a couple of functions. So how do we transition into drive mode? Well, obviously we tell the engine system to activate the engine, and we also change our state to drive. But super important, we must check first that the current state is park, right? Like, this is super important. We shouldn't start driving in any way other state rather than from the park state. And the opposite, if we want to go back to park, same thing, we check we're in drive, we deactivate the engine, and we switch back to park state. So this is easy. Let's clean up the code a bit. Now, very similar. When we want to launch a game, we must check that we're in a park state. This is a super important safety feature. Then we tell the infotainment system, hey, launch the game. We transition to the game state. And when we exit, kind of the opposite thing, right? And we go back to park. So very, very simple. Now, couple other, if we look at the original state diagram, you can see that these four functions correspond with these four transitions, these four arrows. So two more functions we need to implement. One is accelerate. Super important to check that we are in a drive mode first. We should only allow to accelerate when we are we're in a drive mode. And braking, so braking should actually work on all types, in all modes. But notice that when we're in the gaming mode, we want to not only break the actual engine, but also the game. Like when we play in the game, we want the in-game car to break as well. So this is our, like, I'm sure you all are very, very familiar with this, like very comfortable with this kind of code. Simple state machine, we check the state, we do, the operation, we change the state. Really, really boring, really trivial. Cool, so let's take our car on a test drive. But because we are building the kind of operating system for our car, we can't just rely on the UI or like interface. So like we can't just test our car by, trying to tap on the buttons or like, move the gears. Because remember, we are the system engineers. We need our car to be resilient at this deepest, lowest system level, not just relying on UI engineers to not forget to deactivate the button or hide the button. Because, UI engineers, myself included, always make these mistakes, like forgetting to disable the button. That's not a great safety. So it has to be super safe on the deepest information level. Hence why we will be testing our car by hooking up to it using the computer and like sending it commands directly, bypassing all the buttons. So okay, we start we create the car operating system. We tell it, hey, switch to drive. So now we're in a drive mode. Then we say accelerate. The car starts moving. All good. Then we say launch the game. And nothing happens. So that's good, right? Like because we never want to allow to launch the video game while we're on the move. So we brake, the car slows down, we switch back to park. Now when we are in the park, we can try to launch the game again. Now the game launches, we accelerate, nothing happens because we're in the game mode. We can switch back to, and then we try to switch back to drive while we're playing. And nothing happens. So this is great because again, we never want to allow the car to switch into drive and start moving when we're playing the game. We must first switch back to park. Cool. So this is all good, right? But let's get naughty. So let's start here. What if we comment out this check? So remember, in our state machine, we always check what is the current state, we do operation and switch to another state. So what if when we launch the game, we forget to check that we're in a park state? Well, first thing that will happen, well, the code would still compile, right? And this is actually worrying, right? You might not think that it is a problem, but I'm kind of obsessing about type safety and compile time errors. So to me, I make this huge safety mistake and the code still compiles, really bad. So, okay, we make this mistake and we take the car on a test drive yet again. So we start in the park mode, we switch to drive, we accelerate, the car is moving. We try to launch the game. Oh, and now the game actually launches, right? Because we removed the check. That's okay, like just concentrate on the road, ignore the game, fine. Oh, but the acceleration doesn't work anymore. Because remember, we still have the check that we must be in a drive mode in order to accelerate, but we are now in a game mode. So I'm on the road, overtaking the truck, but I can't accelerate. So this is really bad. So I brake and stop to save my life. Okay, the other thing we can do is we can forget to check the previous state, but we can also forget to transition into new state. Same thing, the code would compile, we take on a test drive, we try to launch the game, and the game actually launches, but we are still in the park mode because we forget to switch to the game mode. So what happens now? Braking doesn't work in the game, so like our game is broken now, which is for very weird reason, right? The game is actually fine, but now we're not sending signals to infotainment system because we're in the park mode. And even worse, if while playing the game and we're tapping on the acceleration pedal, we switch to drive, well now the car will actually happily switch to drive and hit in the wall because it thinks that it is in the park mode still, not in the game mode. So this is bad. Now, okay, so let's look at this code. we start in the park mode, we switch in the drive mode, we try to launch the game while driving, and our code right now just nothing happens. But wouldn't it be better, going back to the type state analysis, to actually fail to compile? That the compiler tells us, oh wait, I won't even compile the code because you're doing something totally stupid. You're trying to launch the game while driving. So we can actually achieve exactly that. So let's see how we can do that. And the reason why it's important to get the compilation error and not just like runtime safety is because compilation error is essentially your only real guarantee that undesired change doesn't get shipped into production. Like, think about it for a second. You can have all unit tests in the world. You can have all the linter checks, all your CI. All this is remote, like it's separated from your code, and it can be disabled, muted, force merge, all that. So like you can bypass everything. And admins, when you're in a rush, they can force merge your PR, you can comment out the code, you can suppress the linter rule, you can do all this stuff. The only thing you can't do is to tell the compiler to, bugger off, because it will know, won't build your code. So this is the only real guarantee. How to achieve this? Now, just taking the time, I think we're good. So in order to achieve this, we need to move the type, the state machine into the into the type level. So we introduced three types, park, drive, and game, representing our three states. These are enums without cases because they're simply the type markers. We don't plan to instantiate them in any way. And so our original car definition now has this generic type state. And we no longer need the local variable state because now our state was lifted from the value realm into the type realm. And how do we represent three types is we have the park type is, car of the type park, drive, and game. So this is how we switch between the states. So now, let's now re-implement our four functions. So in order to switch to drive, we obviously tell the engine to start. Now, but how do we check the states? We can't use the state and state to check and reassign a new value. Instead, we use generic constraints. So we only create this function switch to drive when the car is in a park state. And in order to transition to the new state, we must return the new car of a different state. So we start in a car of a park type, and we end up in a car of a drive type. Now, this is kind of insane, right? Like we recreate the car, but remember, the engine system and infotainment systems are reference types. So under the hood, they are still the same systems. So like we don't really recreate the car. We just pass these references to a different value or marked with a different type. So this is how we transition into the new state. So let's clean up all this commented out code. We don't need it. So this is how the transition to the new state happens. And super important, now we can only call the switch to drive function on a park state. For driving and gaming, we actually get the compilation errors because this function doesn't exist even on these types. So I think it's very cool. Okay, let's carry on. That's not all. So the other function that we can call when we're in a park is to launch the game. And very simple, we say tell the infotainment system to launch the game, and we transition to the game state. Now, these are the only two things we can do when we are parked. When we are driving, the only thing we can do is switch back to park. So we can tell the engine to deactivate and switch to park. Very simple. And the only thing we can do while we are gaming is we can exit the game. And we tell the infotainment system to exit the game and transition to the park state. So this is our basic API. Now, important, we must make the initializer private so that we can only instantiate the car by transitioning into a new state. And the only state which we allow to create the car from scratch is the parked state. So now, if we try to instantiate the car, only the parked state is allowed. This is our initial state. And every other state, we move to it by transitioning using one of the functions. So yeah, this is our final API. And again, looking at our state diagram, you can see that these functions, these 5 functions, correspond to our diagram. We start at the park, we can transition to game, back to park, transition to drive, back to park. Now, contrast this to our initial API. Like, I can come to even non-technical stakeholder and tell them, look at the top thing, right? Does it look right to you? And they're like, yeah, yeah. So when the car is in a park state, you can switch to drive or launch the game. When the car is in a drive state, you can switch to park, etc. Contrast this to the original thing. It's completely opaque and lacking any type information. Like, we actually don't know what happens when we call state switch to drive. It's completely opaque. So I think this already is a huge win. Right. We need to implement 2 more functions. One, we need to implement the break. So this is an interesting thing. If we implement this function on the original structure, this will be available for all types. Because we want to be able to break when we park, when we're driving, when we're gaming. And we want a special treatment for gaming only, where we say not only the engine brake has to brake, but the infotainment system also has to brake for the in-game car to brake. So, and acceleration should only be available on the driving car. So, like, again, super important, accelerate function doesn't exist on any other type other than drive. So this is our final API. Let's take another test drive. So we start in a parked car. This is the only way we can start. If I try to accelerate here, cool, I get the compilation error. I can't even accelerate, no such function. I can brake. Now I can switch to drive, which gives me the new variable, and I can accelerate now, so that's good. I try to launch the game while driving. Again, method doesn't exist. Cool, I can brake, I can switch back to park. Okay, now I can switch to game. In-game I can brake for the in-game car to play, but I can't accelerate, again, while gaming, impossible. And I can't switch to drive accidentally as well. So this is mega cool because, you know, we get all these compilation errors. Okay, so the generic APIs like this, well, where we have generic constraints, this also enables this thing I like to call context-aware APIs. And you can see these types of APIs within Swift UI often, or within like libraries such as Swift UI Introspect, where you, depending on the type on which you call the function, it might not be available. So like you can only set the list style on a list type, for example, right? So in this sense, I can chain my functions like this, and this will work. But if I mess up, so if I try switch to drive and then launch the game, this won't work because the upper context doesn't match. So you can actually design really cool APIs this way, you know, using the generic constraints. Cool, okay, but we have one problem. And so we start in the park, we switch to drive, we accelerate, cool. And you know, I can't, like we saw, I can't launch the game while driving, but what I can do, I can reuse the previous parked variable to kind of confuse the system and to hack the system and still launch the game. Because remember, under the hood, these are still using the same infotainment and engines. So this will totally launch the game. So I worked around our super safe API. So this is really bad. And this problem is known as aliasing. In general, in computing, just essentially when you have 2 aliases, or like, you know, one alias essentially is a reference, right? Like we have 2 references, in this sense, driving and parked, to the same underlying type thing, and we can, you know, it's kind of like a shared state thing, so aliasing. So we need to solve this problem. And this is where the borrow checkup comes in Swift 5.9. So I'll give you a quick introduction to this, and tomorrow there will be an in-depth session by Josip, I think. So borrow checker introduces a couple of keywords. One is non-copyable, and a couple of keywords, consuming and consume, and borrowing and borrow. So the best way to understand this is by looking at an example. So say I have a struct file, which I mark as a non-copyable, and it has some do something function. Maybe I read the file, whatever. And then there's a function that takes a file, but notice the consuming keyword. So it consumes the file. Now I create the file, I do something with the file, but then I call this function close, and on the next line I say, oh, do something again, But now I get this great compilation error because it says, well, the file was consumed by the previous line. You can't do this anymore. Alternatively, you can mark the actual function as consuming. This is similar to mutating functions. So this means that self is consumed, right? Like we mutate self, here we consume self. So I could make it as like I tell like, hey, file close. And this would result in the very same behavior. The file consumes itself, right? So let's see how we can use this. So let's mark our car as non-copyable. And going back to our original API, we care about these functions that make this transition, right? Not use the return type, these are transitions. So let's mark all of them as consuming functions. And let's see what happens. So all we did is mark them as consuming and made the car non-copyable. So repeating the same code as before. Switch to drive, now I have 2 pointers, right? Like these are not pointers, but 2 values, 2 aliases, parked and driving. I can't launch the game on driving, but can I reuse parked? Oh, no, I cannot anymore, because the parked was consumed by switching to drive on the second line, right? Like we solved the aliasing problem. So this is really cool. The only way for me to launch the game is to keep using the driving, switch back to park. Now I re-instantiated parked with the new. So like I carry on the evolution of my states. I'm not reusing anything here. I'm switching from driving back to parked, and now I can launch the game. So this is great. So let's see how the compiler sees it, the borrow checker sees it. So let's track the lifetime of the parked variable. So on the first line, it is alive. On the second line, it is dead. It's consumed by the virtue of calling switch to drive. Still dead, hence why we can't call launch again, because it was consumed. Oh, now I reassign the new value to parked. So like by evolving my state, now it's alive again. I can launch the game. Now it is consumed by the virtual calling launch a game, and it's dead again. So like, you see the idea, right? Like the borrow checker keeps track of how parked is used and is not allowing us to reuse it unless we reassign it further down the road. Cool, so crucially, brake and acceleration are not consuming functions. So we can call them many times, which makes sense, right? Like when I'm driving, I can accelerate and brake as much as I want. It's only the switching, the transitions that are consuming. Okay, so, but we still have this problem where we have these 3 variables which we juggle. Parked, driving, and gaming. This is kind of sucks, because what we want is this just normal API where we have like a single variable and we switch between types, right? Like essentially we want polymorphism in this sense, like polymorphism meaning single type on which we call all these different functions rather than different types. So how to achieve these? We don't need any abstractions like protocols. All we need is the enum that switches on 3 states and has the associated values of our, car specialized with the state. So this would be our single interface, and we mark it as copyable as well, and the compiler will actually enforce you to do this because car, park, car, drive, car, game, they are non-copyable. If you have non-copyable associated values, the wrapping enum must be non-copyable as well. And we want the previous old API where we have all these functions listed. So we list all the functions. And you might think that this is the step back, but it is not really. You'll see where we're going here. So let's implement these functions. So init is really simple. The only way to initialize this car state is starting in park. This is the only car which we can instantiate. Now let's implement switch to drive. So because it's an enum, the only thing we can do with it is a switch up on it. But because it's in a non-copyable enum, the compiler will force us to consume self. So this is very important. Okay, so once we switch on self, we actually get access to associated value, which is still the previous API. We are still in this super type safe API that we just built. And the only thing we can do with the parked car in this case is we can switch to drive, get in the new value, but look what happens next. If we stop here, the compiler will give us this amazing error. I freaking love it. It says you missing reinitialization of self after consume. So what this means is the compiler forces us to transition to the next state. Remember where I commented out the transition to parked in the old example? This is impossible now. This is fully enforced by the compiler. And like, I don't have a lot of friends in real life, but the compiler is my friend. Thank you. So let's see how it helps me. So it tells me, you have this problem. And the only thing we can do, this code really writes itself. Like, there's no other way to write this code. We switch to drive, so the only thing we can do is to assign self to the drive state. Like, it's the only thing we can do. And other things, we just kind of plug back again. So like we switch, go from drive to drive game. A bit of a boilerplate, I admit, but the value we get from this, kind of compiler enforced things is amazing. And we can clean up this code a bit by just inlining the transition like this, makes it a bit nicer. And other transitions happen in the same way. So this is switch to drive, switch to park, very similar. The only way to switch to park is going from drive to switch to park. The code writes itself. Launch the game, same, we're in the park, switch to game. Exit the game, we're in the game, we exit the game. So like this code is the only way to write this code. You can't make a mistake. And accelerate and break. So accelerate is only available on drive. So we still get this compile times type save guarantee here. So we just tell the car to accelerate and go back to drive. So like we don't change the time. And break is very similar. It's available on all types, so we just tell every case to break. Now, you might think this like, okay, we made a step back by going back to this like, single API, but this is a very important slide here. What we have on the left is what I would call API, like public application programming interface or public interface. This is what we expose to our users. In this case, we are the car operating system engineers. We expose it to our UI engineers, for example. So they can call these functions all the way we want. What is the important thing, the crucial thing here, that under the hood, what is usually called system programming interface, and actually Swift even has this keyword SPI. Under the hood, we get all this amazing compile time guarantee that, so like our code is, our API under the hood is incredibly safe, both from memory standpoint, reuse standpoint, type safety standpoint. There's no way we call wrong function in the wrong state. There's no way we forget to transition to the correct state. So this is the kind of the crux, right? The most important thing here. And so obviously we can use our single interface and we, do the same thing, but with the single car. In this case, like when we do something stupid, like when we are in a drive mode and we try to launch the game, it again does nothing like before, like where we started. But now at least we know that this interface is powered by this incredibly safe code under the hood at the system level. Right, we're pretty much done. So these are like final slides. So type state, obviously it's a bit niche, right? So when should you consider using it, this approach? Well, when your program behaves like a state machine. You have like specific states between which you can transition, so you want to enforce this transition at the state compile time level. The second, when you have mutually exclusive systems. So in our case, we had engine system and infotainment systems, which we really want to keep separated, right? So this type state allows us to achieve this really nicely. The next thing is perhaps you want to enforce a strict order operations. Remember when we showed the example where the file must be opened first before you can read it. So if you have such use cases, type state is your friend. And yeah, so like this is the same thing. Manage resources with open-close semantics. This could be like files, cameras, I don't know, connections, socket connections, whatever. So quick recap. You can build type-safe state machines using type state. You can build context-aware APIs using generic constraints. Doesn't need to be using like borrow checker. You can just use generic constraints to enforce context-aware APIs. You can control lifetimes of your variables using the borrow checker 5.9. Oh yeah, and yeah, that's the end, really. Let's connect. You can scan this thing, get the access to my social media. I maintain a blog, which is called swiftology.io, where I obsess about types and all this stuff. There's a version of this talk in the article showing a different example using turnstile. You might like reading better than listening, so go check that out. Yeah, that's all really. Have we got time for questions?
Taking shortcuts today. Great presentation. I read your blog post, and I remember when you proposed your talk here. That was amazing.